All right, guys. Obviously, there's been a little bit of a change of plans, basically for the entire week. I'm really sorry that I haven't been there, and I appreciate all of you guys who have put in so much work to still be trying to master the content, even though I really haven't been there to encourage you and to support you. So I should be back next week. Things are getting sorted out and getting figured out a little bit. So I anticipate that next week should go back to normal. But in order to thank you guys for all of the support that you guys have given me this week, I have a quiz because that's how I show that I care about you guys. So this quiz is going to be focusing on a particular skill that I know a lot of you guys have struggled with, which is those kinds of questions that say, all right, we set this up this way, and then we double something, or we half something, or we quadruple something, or we somehow change something about the original problem. How does that change this other variable? These questions are called factor of change questions, or the AP, the College Board kind of calls them semi-quantitative thinking questions, which is to say that they're questions that require some math, but don't really require as much math as they seem like they do. So we're going to work on this drill quiz, and I'm hoping that even though it's going to be as similarly awful as the last drill quiz was, by the time that we're done, you'll walk out of it feeling like you're better at this than we were when we started. So these ones are a little bit longer. So I'm going to be giving you guys 90 seconds per problem. And then after that, I will review it. Obviously, this is this is a little bit fake. You guys are in control of this video. So if you take more than 90 seconds, I will have no way of knowing. If you guys skipped my answers, I'll have no way of knowing. And that's not the point. The point is to try and do this, to try and get it done in the 90 seconds, and then watch my review and how I do that. Take some time to master the skill, and then move on to the next question, feeling a little bit more confident, a little bit more comfortable with how to do these problems. So that's the general idea. From here, you should advance to your next slide. You should go to the very next one. Here we go. Okay, on this slide, this is not to the factor of change yet. This is just some review for some of the formulas. So very quickly, let's give you guys about 2 minutes. Take about 2 minutes and just connect all of these with lines. Connect the equations to what the equations are used for. Again, you have about 2 minutes. I am doing a timer in the corner, just so you're aware. Please don't stare at me. Please just do this. But I am just going to sit here awkwardly and stare at you. To be fair, you're the one who's awkwardly staring at me. I can't actually see you right now. You have a minute left. Keep drawing those lines. Great job. Hey, that one was correct. I'm proud of you. You keep it up. Way to go. I don't know about that one. That's better. 30 seconds remaining. You're doing great. You got 20 seconds left. Let's get those last couple lines done. Uh-huh. All right. Wow. If you haven't heard it before, I want you to know I'm proud of you. Okay, that was time. So I'm just going to go to the next slide. I've already done this, so you guys don't have to watch me draw lines. But here are the answers. If you feel like you need to pause it right now just to go back and double check yourself, that's totally fine. Go ahead and take that time. So I'm hoping you've already double checked your answers and seen what you missed. But just to run down the list of variables here, our formula at the very top, that is a formula for it's a kinematics formula, but one that uses only time. It doesn't care about distance. Our next formula is an equation, again, kinematics, but this one has both time and distance in it. Then we have our third kinematic equation, which deals only with distance, has no time in it at all. Then we have kinetic energy. We have the force of a spring. We use this F equals kx equation when we are looking at a system that's in equilibrium, a, um, a mass that's just hanging but not bouncing or doing anything from from a spring. Or we might use it if we're trying to find the instantaneous acceleration. But we don't use this equation for moving springs and trying to figure out what their velocities are. Instead, we use the next equation, spring potential energy, and we set up energy equations to figure out like kinetic energy and the velocity at that point. But we can't use this equation, the US equals 1/2 kx squared, to find the acceleration. So we would use the formula above that for that. Then we have gravitational potential energy. Our next two equations are period equations. They're how long it takes for an oscillation. The first one, T sub S, would be the period of a spring. And then T sub P would be the period of a pendulum. And then finally, we have the force of gravity equation, G m1 m2 over r squared. That one's kind of a throwback equation. We haven't really used that one at all in this unit, but it seemed like something we could throw in here in practice. Okay, so now I'm going to start going to the problems. Again, you will have 90 seconds on these problems. So work quickly to answer them, and then I will review after each one. All right, so we have a student pulling a spring back 15 centimeters. Oh, my camera's gonna be in the way. Let's move that down. Uh, Pulls it back 15 centimeters with a 400 Newton force. He then pulls the spring back 30 centimeters. How much force would be required? You have 90 seconds. Actually, you have less than that now. Fifty seconds remaining. Thirty seconds remaining. 15 seconds. 5, 4, 3, 2, 1, 0. Okay, so you should stop here. It doesn't matter if you get these right. This quiz actually isn't real. The only reason we're doing this with the time pressure is to help you practice doing this quickly. So hold yourself accountable to the 90 seconds. And now we're going to move to the next slide. And on this next slide, I'm going to show you the work of how to get the right answer. So move to that next slide. You're going to record your score here. It's not a big deal. Who cares? I'm going to move my camera one more time. I think I'm going to put it in the bottom corner. That's better. So the first thing that we're going to do for all of these problems is we have to identify which formula we should be using. This is talking about a spring, and it's talking about pulling it back and kind of holding it there. So this is going to be our equation, F equals Kx. So our first job is always going to be to identify the equation that we should use. Some problems actually use more than one equation. Everything in this quiz is only using one because I'm just practicing this skill. But be aware that on the AP exam or on your exam in a couple weeks, you'll probably have some that require you to combine one or more equations. Okay, So this is the equation that we're using. And I'm not going to plug the numbers in, even though I totally could. Instead, and one of the reasons why it would kind of waste time to try and solve for k. Instead, I'm going to use the factor of change method. Now that I've found this equation, I'm just going to describe how each number is changing. So one thing that's changing is I'm going from an x of 15 to an x of 30. That is changing by a factor of 2. But it's the same spring. There's no reason for us to think that the spring is changing, so the spring constant is not changing. So then if I plug in those factors of change, my k is not changing at all, my x is doubling, then you can see that when I evaluate this, the right side of my equation has gone up by a factor of 2. That means the left side of my equation also has to go up by a factor of 2. And if I was originally 400 newtons, now that I'm doubling that, I would be up to 800 newtons. So that's the correct answer. Just to review and to kind of go through the quicker, like the way that you want to be solving these so you're going really, really quick, what I would have done is I would have just said, okay, F equals Kx is my relationship. My K is not changing. My X is changing. It's doubling. That means that my force has to double. If my original force was 400, now it's 800. And there's your answer in hopefully way less than 90 seconds. Okay, so that's how we did the first one. If you didn't get that one, no big deal. This first one was kind of a practice one for us to learn how to do the factor of change. So if you need to, rewatch this part of the video again to make sure that you're really sure of how to do this skill, and then let's do the next one. All right, next question. Again, you'll have 90 seconds. A student has a cart that's moving with a velocity of 5 meters per second, and it has a known kinetic energy of 1200 joules. If we double the velocity, what is the new kinetic energy? You have 90 seconds. That was an elevator. You have 1 minute remaining. Thirty seconds remaining. Fifteen seconds. You can do this. Wrap it up. All right, that's time. Hold yourself accountable. Stop where you are. We'll go back, we'll review this, but let's make sure we get an accurate measure for how you're doing right now. All right, so going to this next slide where you guys are going to record your scores. I'm going to do the work. You should follow along with me. Make any changes that you need to, or write it down and figure out what steps you're not understanding. All right, first thing that I'm doing is I'm going to figure out my formula. This is something that's talking about kinetic energy, so we should just jump straight to our kinetic energy formula. That's K equals 1/2 mv squared. Our next thing that we're going to do is we're going to figure out our factors. What's changing, what's not changing. The factor that's definitely changing is I'm going from an initial velocity of 5, and then we're doubling it. In fact, that just told me right there the only factor that mattered. Yes, I'm going to 10, but who cares? It just told me what the factor was. Sounds like it's still the same cart, so this is just going to go from m to m. That part's not changing. Now, our last step is we're just going to solve this. We're going to plug in those factors of change, and we're going to figure out what the answer is. So our equation is k equals 1/2 mv squared. I'm going to plug in my factors. My m isn't changing. My v is doubling. But remember that it's not just about v, it's about v squared. So anything that's happening to v mathematically, I still have to do to it. You can see that I'm still multiplying it by my m. That just didn't change. I'm still even multiplying it by the 1/2, but the 1/2 doesn't change either. It's a constant in this equation. So you can either just not worry about it ever, or you can just put in a 1 there as well. Okay, so I have no change to my 1/2, no change to my m, but my velocity is doubling and I'm squaring that. So on the right side of my equation, I'm going up by a factor of 4. That means I need to go up by a factor of 4 on the left side as well. If I was at 1200, I'm at 1200 times 4. So the answer is 4,800 joules. Awesome. Let's go to our next one. Again, you'll have 90 seconds. If you need to, though, pause this, go back, and make sure you're comfortable with doing this. If you can get the first 2 wrong, no big deal, but it would be awesome if you can now get the next 8 right. Here's our new problem. Objects being dropped, taking 3 seconds to hit the ground. If the height's increased by a factor of 4, how long is it going to take to hit the ground now? All right, go ahead. You have 90 seconds. You have a minute left. You have 20 seconds left. All right, that's our time. So we're going to go to the next page. Just stop where you are and let's see how you did. First thing we're doing is we're picking our equation. This is something that's being dropped and we've been given a time and it's talking about a height. That tells us what equation we're going to use. If distance and time were discussed, it's going to be this one right here. But for this one, we're going to have to do a little bit more work because there's a lot of variables in there that we want to get rid of before we go to our next step. We want to simplify this down so it's an equation that's more useful to us. Oops, there should be a T there. Cool. So if it's being dropped, we can say that the initial position is 0 and get rid of that term. And if it's being dropped, we know its initial velocity is 0, so we can get rid of that term as well. So now our formula just looks like this. X equals 1/2 at squared. But it's not actually asking about x. And this is where the formula gets a little weird. The question's asking about t. So we have to put some work in here. We have to solve this for t. I'm going to multiply both sides by 2. That's 2x equals at squared. I'm going to divide both sides by a. That's 2x over a equals t squared. And then I'm just going to square root both sides. All right, so the step to get our formula was a little bit longer because I had to put it into terms of the variable we cared about, which was time in this case. So there was some cleaning up steps that didn't exist in some of our previous problems. But now that we are here, which was definitely the longest part of this process, now we're just going to plug in some very simple factors. The factor that's changing is that the height's 4 times higher. So when I plug these in, my 2 is not changing. My x is 4 times higher. I'm still on the same planet, so my acceleration is exactly the same. But I have to remember that this whole thing is being square rooted. So I still have to apply those mathematical operators, things like squares, square roots, sine, cosine. Those things aren't constants that you would just like plug in a 1. They're mathematical things we're doing to our numbers, and we have to keep doing those with this factor of change method. So this simplifies down to the square root of 4, which simplifies a little bit further down to 2. That means that we changed the right side of our equation by 2. That means our time is changing by a factor of 2. And if we were originally 3 seconds, now we're up to 6 seconds for our answer. All right, great work. I hope you got that. Otherwise, again, I suggest you stop this, you go back, try it again, see if you can figure it out, see if you understand the reasons why we're doing what we're doing, and then move on. We've only done 3 so far. You still have a chance to just absolutely crush 7 of them. And it's worth doing so that then when we get to the exam, the next exam, or a quiz that has these kind of questions on them, you can just start getting these right consistently, and your grades will go up. Okay, next question. Again, you'll have 90 seconds. Mr. Terrell standing on a planet with twice the radius and twice the mass of Earth. If I weigh 650 newtons on Earth, what is my, oh, that should actually say weight, my mistake. That should say, what is my weight on the new planet? So that should say weight. You have 90 seconds left. Remember, first step, find your formula. You have a little bit less than a minute left. Start plugging in those factors of change. What numbers changed and by how much did they change? You have 20 seconds left. Make sure you simplify that, and whatever change happened on the right side is what's happening on the left side. 5 seconds, get your answer in. All right, that was time. Hoping you feel confident on that one. You're feeling like you're starting to get it. So step 1, let's figure out our equation. This is something that's talking about planets, radiuses, mass, weight. It has to be this force of gravity equation. That's the only one that has the right variables. And if we're talking about things like weight, it should be a force of gravity equation. So we're going to be using Fg equals gm1 m2 over r squared. Cool. I hope you were able to identify that. Now we're talking about the factors that are changing. The factors that are changing is that the mass of the Earth is doubling. So this is going to be going up by a factor of 2. And the radius of the planet is going up by a factor of 2. So when I plug in my factors of change, I have m2 doubling. I have radius doubling. When I plug them in, it's going to look something like Fg equals, all right, my big G is not changing. My mass of Mr. Terrell isn't changing. He's still the same guy, no matter what planet he's on. But the mass of the planet, that one there, is doubling. So I'm doubling it right there. Then the radius of the planet is also doubling, but I have to preserve that squared. Don't forget that squared isn't a variable that would be constant. It's a mathematical operation that has to stay in here. So when I simplify this down, this becomes 2 over 4, or 1/2. I just changed my right side by a factor of 1/2. That means I have to change my left side by a factor of 1/2. So if it was 650 before, now it's half of that, or 325 newtons. All right, that was number 4. I'm hoping you're starting to get an idea of the process, even if some of these are still showing off some new things. Like this one here had 2 variables changing. I'm hoping that you're starting to see some of the commonalities here so that you can start getting these consistently correct. All right, let's move on to the next one. Again, you'll have 90 seconds. Student sets up a pendulum with a length L and a mass M. She times the period, finds that it is 2 seconds. If she doubles the mass, what would be the new period? You have 90 seconds. First thing, figure out what equation you're going to use for this. What equation matches this problem? Okay, about a minute left. Figure out what variables are changing. "30 seconds. You should start simplifying here, figuring out your answer. Five seconds. Make sure you get your answer in. And that's time. Let's stop here. Let's look at how you guys did. So the equation that we're going to use here is the period of a pendulum. That's 2 pi times the square root of L over G. It's this guy right here. Now what you might notice is the only variable that we talk about changing is the mass, and there is no mass in this equation. So this one should have been super fast. We're not changing any of the 2 pi variables. We're not changing the length. We're not changing the gravitational acceleration. In fact, we're not changing anything. So everything on the right side simplifies down to 1, which means the period is still just 2 seconds. This goes back to a really important lesson that I want you guys to learn about the period of a pendulum, which is it's not based on mass at all. All right, so that one wasn't meant to be a trick question, but it was meant to help highlight one of the big misconceptions that comes up with pendulums. So I hope that if you did make a mistake, you learned where your mistake was. Next question, again, you'll have 90 seconds. All right, a penny's being dropped from the second floor window. We know how much potential energy it has. Now, if we have a quarter, and we're going to be generous and say it's exactly double the penny's mass, if we drop it from the 100th floor window, how much potential energy would it have? And again, we're going to make an assumption here that the floor heights are consistent. All right, I just started the timer. I'm not going to say anything else about what steps to do. It's on you guys now. Good luck. You guys have a minute left. "30 seconds left. 10 seconds. Get your answer recorded into the pear deck. All right, that's time. So moving on to our next slide. The equation that we're going to use here is we're going to use gravitational potential energy. So from here, we're going to figure out the factors of change. Well, we doubled the mass of the quarter. The acceleration stayed exactly the same, so that's a factor of change of 1. And then when we're dropping it first from the second floor, but then we changed it to the 100th floor. That's 50 times higher, so our factor of change is 50. We went from 2 to 100. We're looking at the factor of change, not the difference. So that's a factor of change of 50, not a numerical difference of 98. So if you made that mistake, we're looking for what we multiply by to get the new value, not just the difference between them. Okay, so when we evaluate this, this is 100 times greater. So I'm just going to take 0.2 times 100, and that works out to be 20 joules for the answer. Awesome. All right, let's move on to our next one. I think we have 4 more after this, so we're getting close to being done. All right, we have 90 seconds. All right, Chloe's still playing with pendulums. She just absolutely loves them. So remember that her first pendulum had a period of 2 seconds. If she made the length of the pendulum 9 times longer, what would the new period be? You have 90 seconds. All right, 1 minute left. Thirty seconds remaining. Ten seconds. All right, so that should be it. Wait, for some reason I feel like I'm on the wrong slide there. All right, well, this is the slide I'm on. Okay, so let's look through this one. Again, this is the period of a pendulum. I don't know why, but often when I'm doing things involving periods, I just use a red marker for no reason at all. So let's just use this red one right here. Here's our equation for the period of a pendulum. And then we're just going to go through and we're going to apply our factors of change. Now this 2 pi is just a constant, so that's always going to be a 1. It literally can't change because the values will always be 2 and pi. But within here, now we have some variables that could change. Our L is getting 9 times longer. Yeah, so we have a factor of change of 9. But no reason to think that the acceleration due to gravity has changed. So that would just be a factor of change of 1. So if I evaluate this, this is changing by a factor of 3. That's the square root of 9. And so that means that the period is now 6 seconds long. And that is our answer. Awesome. All right. I'm hoping that you're finding that you're getting these right, or you're feeling like you're understanding them more and more. And it would be awesome if you're starting to get really annoyed that I'm giving you guys 90 seconds. I am super bored waiting 90 seconds. tough. All right, next one. Here we go. 90 seconds. Car takes 40 seconds to stop from an initial speed of 10 meters per second. If it's moving at 5 meters per second, now how long would it take to stop? 90 seconds. One minute. Thirty seconds. Ten seconds. Make sure you get your answer written down, put it into the pear deck, and let's get ready to move to our next slide. All right, that's time. Let's move to your next slide. This is the orangish slide where we're going to record your scores. Okay, so the equation that we're going to do here, it's talking about time. We have 40 seconds there. It's talking about speed, so this is kind of sounding like a kinematics problem, but I don't see anything about distance at all. So that means it's going to be this equation here, the one that has only time in it. Let's see, we're trying to get it to stop, which means this guy's 0. So we know that. And the question's really asking about how long it takes. So I'm going to solve this equation for t. Let's say t equals v naught over a. Okay, that's the formula that we need to use for this. For some of these problems, like you've noticed, we can just use the formulas as is. Other ones, we have to manipulate a little bit so that we can solve them for the variable we care about, in this case, the time. So now we plug in our factor of change. The factor of change is we're going from 10 to 5. That's a factor of 1/2. Going from 10 to 5, we have to multiply by 1/2 in order to have that happen. So my v naught is going to be 1/2, but we're assuming the acceleration is the same. So then the factor of change for the acceleration is 1, which means that the right side of our equation changed by a factor of 1/2. That means the left side also changes by a factor of 1/2. And so this is going to take 20 seconds. That is our answer. It was 40 seconds, but if we change the right side by 1/2 by halving the velocity, that seems weird. By multiplying the velocity by 1/2, we have to also multiply the time by 1/2, and we drop down to 20 seconds. All right, we only have 2 left. So next question, again, 90 seconds. Period of an oscillating spring is 10 seconds, using a spring with spring constant 1000 Newton meters. If we used a spring with spring constant 250, what would be the new period? You have 90 seconds. 30 seconds remaining. Five seconds. Get your answer in. All right. So the equation that we're going to use is we're going to use this one right here. Equation for the period of a oscillating spring. We're going to plug in our factors of change. The 2 pi isn't changing. Those are constants. The same mass is used, so the factor of change for m is 1. But we're going from 1,000 to 250. That's our factor of change of 1/4. All right, here's where algebra gets a little bit tricky. A 1/4 in the denominator would be the same thing as a 4 in the numerator. So then we're just changing the right side by a factor of 2. If it was 10 seconds, now we're up to 20 seconds. I feel like it's ended up 20 seconds for a couple different things. That's just a coincidence, but interesting. All right. Oops, I was supposed to go to this slide for that one. My mistake. All right, our very last question. Again, you'll have 90 seconds. Chloe, she just can't get enough of her pendulum. She went back to the original setup. The length, we'll call it 1 meter. But she just teleported to the moon with an acceleration due to gravity of, oh, that's so embarrassing, of g equals 1.0 meters per second close enough. Can you guys find how long the string has to be to keep the period constant? You have 90 seconds. I'll tell you the tricky one here is we're not solving for, we're going to have to manipulate the equation a little bit. All right, good luck. One minute left. Thirty seconds remaining. Last 5 seconds. Try and get your answer into the pear deck, please. And that's time. All right, so going through here, the equation that we're going to use is still the same equation for the period of a pendulum. The tricky part here is that we don't care about t anymore, we care about L. So I'm going to have to manipulate my equation to get L all by itself on one side and all the other stuff on the other side. So I'm going to do that by first dividing both sides by 2 pi. The next thing I'm going to do is I'm going to square that entire side, or both sides. So that would be t over p, or tp over 2 pi squared equals L over g. And then my last step is I'm just going to multiply both sides by g. So I get tp over 2 pi squared times g equals L. And now we can apply the factor of change. And what's cool about this, now that we've done this, this work to get to this equation, this part's very easy. We're not changing the period. We want to keep it the same. So the factor of change for the period is 1. 2 pi, yeah, that's not changing either. So that whole quantity is squared, but that's just going to be 1. The thing that's really changing here is G. We're going from G equals 10 to G being equal to about 1. That would be a factor of change of 1/10. That means that if this whole side changed by a factor of 1/10, then L would have to change by a factor of 1/10. So the length of our pendulum on the moon that would have the same period would be about 0.1 meters or about 10 centimeters. All right, that's it for today. That's the whole quiz. So I hope that this drill quiz felt like it was successful to you. I hope you feel like you learned from it. I missed all of the really nasty private messages that you guys sent me on Monday. I wish that those had been able to get to me today. But I'm hoping that this was something that felt useful to you and helpful to you. Again, I do want to say thank you to all of you guys who have sent me really, really nice emails, just telling me to take my time and all that kind of stuff, and all your thoughts and prayers and stuff that you've expressed towards my son getting better. I really, really, really appreciate that. You guys are awesome, and it's so nice that you guys took time out of your day to send those kind of messages to me. That said, hoping to be back on Monday. On Monday, we start our new unit of momentum. So I want to encourage you guys to wrap up everything that we did this week. Make sure you watch all the videos, you do all the pair decks, and you either get really, really solid on that stuff on your own, or please set aside a list of questions. I will definitely make sure that I have office hours for you guys next week. And I would love for you guys to come in. If you were stuck and you just couldn't figure out how to solve one of or to do one of the assignments this week, and I wasn't around to help you guys out, please save that, make a note so I can help you with it next week. I really want to make sure that you guys still learn this stuff. I'm really sorry that I wasn't able to be there for you guys this week, and I really appreciate all of your patience. So that's it for class today. Just finish up the rest of your independent work and have a great day. Thank you.